Centripetal acceleration, both the direction of the centripetal acceleration and also the magnitude of the centripetal acceleration. So we're going to consider an object moving in uniform circular motion. Capital R is the radius of the circle, and in the development here we're going to write down the radius vector, that starts at the origin and goes out to the object, in x and y components. And we'll use the I hat and j hat unit vector notation. So I'll have a drawing here that you'll see in shortly. We're going to take the derivative of the radius vector as a function of time. That will produce the velocity. And then we'll take the derivative of the velocity vector. That will produce the acceleration vector. And then we'll be able to deduce the direction and magnitude of the centripetal acceleration. So here's our drawing and a little start here. So we have an object that's at this location on our circle right here, and it's moving counterclockwise, or the standard direction for positive angle, this omega, and it's on a triangle. So at that point, the radius vector is the hypotenuse. The length of the radius vector is capital R, the radius of the circle. This radius vector has an x component and a y component. And r sub x would be r cosine theta. R sub x is adjacent to the angle, so the cosine theta is the correct choice there for the calculation. R sub y is opposite to the angle. So hypotenuse multiplied by sine of theta gives us the length of that opposite side. Theta itself is calculated by taking omega and multiplying by time. Omega is in radians per second. Time is in seconds. Those units cancel, and we get theta with the units of radians as we should. So here's our radius vector as a function of time. Here's the x component. Instead of theta, we see omega t. I hat. I is the unit vector, has a magnitude of 1, points in the x direction. J hat is the unit vector in the y direction. Again, magnitude of 1 gives us the direction for this term along the y-axis. Now, in this development, I'm going to be taking the derivative of sines and cosines. So just a quick little review of the derivative. If I have some constant a and cosine omega t, derivative with respect to t, the a is just repeated. Nothing happens when I take the derivative here to the a value. It repeats. I won't get into all the calculus technicalities. Talk to your instructor if you have some questions on what's happening here. We have to take the derivative of the argument of the function. So the derivative of omega t with respect to t, that just leaves us with a factor of omega. And then the derivative of cosine produces minus sine function. So this minus sign, this minus sign, is produced by taking the derivative of the cosine function. And then the argument is still omega t. So that's the proper calculus treatment of derivative of cosine. Similar thing for the sine function, but now the derivative of the sine function produces a plus sign, plus sign, and again the derivative of omega t with respect to t produces the omega. So you need that information to handle this next step, which is taking the derivative of the radius vector to give us the velocity vector. So our constant here is r, that survives. The derivative of omega t with respect to t gives us omega. The derivative of the cosine function produces this minus sign and the sine function. The derivative of the r sine omega t function, we get r omega. There's an omega squeezed in here. Sorry, almost forgot to write it in. The sine function switches to cosine, and the term is still positive. That's the velocity. Now we take the derivative of the velocity. What will happen in this term when we take the derivative of the velocity? What will happen in this term when we take the derivative of the velocity? sine function here, cosine function here. Well, we're going to get an extra factor of omega. The derivative of omega t produces another factor of omega, so we get an omega squared. When we take the derivative of the sine function, we don't change the plus or minus nature of the term, so we still have a minus sign, we still have the r. Sine function switches to cosine. Here, again, we take the derivative of omega t, that gives us another factor of omega, and because we're taking the derivative of the cosine function, the term reverses its plus minus sign, now minus. Again, the derivative of cosine is minus sine. So there's our acceleration vector. I want you to take a look now at the acceleration vector and the radius vector. Do they have any similarities? The acceleration vector and the radius vector, are they similar in some way? If you look at the x component, the I hat term, I see a cosine omega t, I see a cosine omega t, I see an r, I see an r. But I've got something extra down here, minus omega squared. Same thing here, sine and sine, r and r, but a minus omega squared factor that's not in the r term. So I can say that the acceleration vector is minus omega squared times the radius vector. What's it mean when we have a minus sign for a vector? The radius vector has a certain direction. That direction is from the center of the circle to the point where the object's located. R is from the center of the circle to where the object is located. What's it mean to have a minus sign in front of a vector? Well, it means that we reverse the direction. The direction of A, the acceleration, is opposite to the direction of R. The A vector points towards the center of the circle. A is centripetal. This acceleration is centripetal. And in the picture, we have just one location, but this happens all the way around. Doesn't matter what the theta is, what the time value is. The acceleration vector is always going to be in the negative direction of the radius vector. So, in fact, this acceleration is centripetal. What about the magnitude? Well, a little bit of side work, probably you could say here. The magnitude of the radius vector, it's obvious from the drawing. If you can see the drawing, it's obvious from the drawing that the magnitude of the radius vector is always capital R. We're on a circle. But let's just confirm that here. R would be the square root of the x component squared and the y component squared. Those squared become r squared cosine and r squared sine squared. If I factor out r squared in here and then apply the square root to it, I get an r out in front. I'm left with cosine squared plus sine squared. What is that trig identity? Pretty important identity in trigonometry. Cosine squared plus sine squared, they have the same argument. That's a 1, and the square root of 1 is a 1. So the magnitude of the radius vector is capital R. Now take advantage of the fact that there's a connection between the linear velocity, v, and the radius of the circle, capital R, and omega. V is equal to R times omega. So I have here from up above that the acceleration and magnitude is different than the radius vector by omega squared. I'm going to substitute in and replace omega squared with v squared over r squared. If you would solve this for omega, off to the side here, if you'd solve this equation for omega, you get v over r. If you square that, you get v squared over r squared. And then down here, one factor of the r cancels, and I'm left with the formula for centripetal acceleration. The magnitude of centripetal acceleration is the square of the velocity, or square of the speed, that's all you'd really need, divided by capital R. The velocity does have speed and direction. The velocity is always tangent to the circle, but we square that number of meters per second, we divide by the number of meters in the radius of the circle, and we get the magnitude of the centripetal acceleration. So the tools of calculus here have provided us both the direction and the magnitude of the centripetal acceleration. The key part is when you recognize that after you've done the derivative on the radius vector twice, you get a same mathematical form for the acceleration vector as the radius vector. Only differs by the factor minus omega squared. From there, you get the direction is centripetal, and the omega squared with the magnitude of capital R for the radius vector provides us with a sub c is v squared over r. So you might want to go back, pause the video at certain locations, and make sure you understand all the manipulations that were done. Ask your instructor if you have questions.